I'd like to talk about two more tests for infinite series, the comparison test and the limit comparison tests. So first of all, let's review. Two series that we know about, the p series. So that's when you have 1 over n to the p. We know that converges if p is greater than 1, and it diverges if p is less than or equal to 1. Okay. And then we also know about the geometric series. So this is where you have a constant ratio between the terms of the sequence. And so this will converge, right, if that common ratio is less than 1, right? In absolute values, it can be an alternating series. And then it diverges if that ratio is greater than or equal to 1. So we need to have these two series because that's what we're going to use to compare with, because these are the things that we know. So let's talk about the comparison test first. So the assumptions we're going to make is that a sub n, well, both a sub n and b sub n are positive, and that a sub n is less than or equal to b sub n, all of those terms, right, at least at some point. It doesn't have to be for every value, right, at the beginning, but at some point you're going to reach an n value where all of those a sub n's are less than your b sub n's, right, at some point and then from then on. So here's how the comparison test works. So when this inequality holds, if we know that b sub n converges, then we also know that a sub n converges. And let's see why that makes sense, right? So I know that my a sub n's are always less than my b sub n's, and I know that my b sub n's converge. So that means that series of a sub n's, right, has an upper bound of whatever b sub n converges to, so then a sub n will also converge. Likewise, we know that if a sub n diverges, then our b sub n will also diverge, right? Because it's bigger. Right? So if I know that this smaller series diverges, then anything that's bigger than that will also diverge. Okay, well, let's go ahead and practice. We're going to determine if the series converges or diverges, and we're going to use the comparison test. So when we do these tests, we kind of have to have an idea going in of what it's going to do. So we're going to take a guess at what we think. With a lot of these tests that we do with our infinite series, there's going to be okay, what do I think? And then we're going to choose a test, and then we're going to try the test. And sometimes it's not going to work. Sometimes that test will be inconclusive, and we'll either have to try it differently or try a totally different test, okay? Okay, and I didn't even, let's check the divergence test real quick, make sure our nth term goes to 0. Right, so as n goes from 1 to infinity, right, I'm dividing by infinity, so yes, my nth term goes to 0, so I know I have to keep going. So now, right, I'm looking at this, and it kind of feels like a p-series, right, and it feels like I could compare this one to a p-series. This is similar to a p-series where p equals, right, 3/2. So this is going to behave a lot like 1 over the square root of n cubed for big N, right? And 1 over the square root of n cubed is 1 over n to the 3/2. Okay, so let's see how that comparison test works. So we think, right, here's how it goes. Here's our thought process. So this means it's going to converge, right? So we're going to look at the converging line. Okay? So if b sub n converges, then a sub n converges. So b sub n, this thing that we know converges, if we can show that we meet our assumption that it's always greater than or equal to this other series we don't know about, then we can say something about our b sub n that we don't know about. All right, so can I show that this series that I know, 1 over the square root of n cubed, is always, or at least always past a certain point, greater than or equal to the terms of this series that I don't know? Oh, I always put that cube there. So square root of n cubed plus 5n minus 1. Okay, so now we need to manipulate this inequality. So, right, one of the inequality rules is we can square both sides. So let's go ahead and do that. So that's going to lead us to 1 over n cubed plus 5n minus 1 less than or equal to 1 over n cubed. And we can multiply both sides by the common denominator in order to clear the fractions. So that, well, it's essentially cross multiplying. Leads me to n cubed. Is that less than or equal to n cubed plus 5n minus 1? Okay, I don't know. Let's keep working it. So subtract n cubed from both sides. We'll get 0 less than or equal to 5n plus 1. I'm sorry, minus 1. Add the 1 to both sides. Hey, there we've got it. 1/5, like less than or equal to n. So this inequality, back up here before I squared, so I'll put the square roots in just so you can kind of see. This inequality is true for all n greater than or equal to 1/5. And since we know that 1 over the square root of n cubed converges, because it's p-series with p greater than 1, then we know that our other series, n cubed plus 5n minus 1, also converges by the comparison test. Okay, so we went into it thinking it was going to converge. So then we had to come up with a series that we knew converged and show that the one that we didn't know about was always less than or equal to that. Okay, so let's do another one with the comparison test. Hold on, I'm going to grab that out so we can't see so much underneath. Okay, so now we're looking at sine squared n over n squared from 1 to infinity. So now, right, we're going to think. What do we think is going to happen here? What does this kind of look like? Okay, so I'm thinking p-series again. And think about the values that sine can take on, right? So we know that sines, all right, bounce back and forth between plus or minus 1. Since I'm squaring it, that's going to keep me on the 0 to 1 side, right? Keep them positive. I'm not going to get bigger than 1. So I might choose, right, something. So I'm thinking, I think it's going to converge, right? Because that top's not going to get very big and this bottom is n squared, so I have a p-series with n bigger than 1. So if I can show, right, the way we use our comparison test, okay, so if we think it's going to converge, then I need to, right, come up with a b of n that's always bigger than a of n, right, and show that if b of n converges, then my a of n will converge. Okay, so the b of n that I'm going to choose then is 1 over n squared. So is it true that sine squared n over n squared is less than or equal to 1 over n squared? Well, it is. So, right, we could multiply out our n squared. So then, is it true that sine squared n is always less than or equal to 1? And it is, right? You can check that on the unit circle. You could square root at both sides if you are wanting to go one step further. Is it true that the sine of n is less than 1? Yes. Right, definition of, right, your trig functions. So, since, we're just going to write it up then. Since sine squared n over n squared is less than or equal to 1 over n squared for all n, and since the series of 1 over n squared from 1 to infinity converges, this series that's always less than or equal to it, sine squared n over n squared, also converges. Now, when you're writing these out, right, for your instructor, you're going to want to have all of these pieces, right? You can't just say converges like it's magic, because then it's just, right, a 50-50 chance that you got it right. You need to show how you came up to that realization. So this last little bit, it's kind of like those delta epsilon proofs, but not nearly as bad. Right? You're just going to kind of write it up about how you came to your analysis. Okay, so now let's do one that we think is going to diverge. So we're looking at this new series. I'm going from 4 to infinity just so I don't get an asymptote. And I have square root of n over n minus 3. Right, so this time when I look at that, I'm kind of thinking it's going to diverge. Just because, right, it kind of feels like it's a 1 over square root of n. So I'm thinking, I got a feeling this is going to diverge. Okay. So if I think that it's going to diverge, then I want to find a function, right, that's always smaller than it, that diverges. So, I'm sorry, your if-then statements will only work one way, so you kind of have to be careful. So if I can find a series that's always smaller than the one that's given, and it's a series that I know diverges, then I can say something about b sub n. Right, so they only go, if I know this A, then I can talk about B. It can't go the other way. Okay? If-then statements go one direction only. Only when you have the if and only if can you go either way. If you get one, then you get the other. Otherwise, it's a one direction. Okay, so since we're thinking diverge, I need to come up with an a sub n that's always less than or equal to your b sub n's. Okay, so this is a little bit different. This time this is our b sub n here, right? And we're going to think of an a sub n that diverges. So, right, that a sub n that we'd look at would be 1 over square root n. We know this one diverges p series, where p equals 1/2, less than 1. Sorry. Okay. So can I show that this diverging function series is always less than or equal to this series that I don't know? Well, I don't know. Let's work on this inequality. Okay, so multiply both sides by square root of n. So that leads me to a 1 on the left, less than or equal to n over n minus 3. Multiply both sides by n minus 3. So now I have n minus 3 is less than or equal to n. Go ahead and subtract n from both sides. Oh, okay, the n's all went away. But what I'm left with is a true statement. Negative 3 is always less than or equal to 0. Right? This is true for all n. Right, because the n's go away. So if what you're left with is true, that means it's true for all n's. So we've done it. We've shown that the inequality holds. There's your original inequality. So this is true for all n. See the work below. And the series 1 over square root n diverges. So we know that the series that's always bigger than that also diverges. Okay, so that's the comparison test. Now, just to be especially obnoxious, we're going to do another one called the limit comparison test. Okay, so here are our assumptions. So a sub n and b sub n just have to be greater than or equal to 0, right, for all of your n's greater than 1. If the limit of the ratio of a sub n over b sub n equals L, and L is not 0 and L is not infinity. So you take this, right, you compare two series. Right? You're going to take the limit as n gets big. If that limit goes to just a number, right, a finite number, then the series of a sub n and the series b sub n both converge or diverge. That means they do the same thing. Okay? So the way we're going to use this, right, is we're going to be given an a sub n. We're going to come up with a b sub n that we know what it does, right? We know that it converges or we know that it diverges. We're going to do a ratio. We're going to take a limit. If we get that limit to be a finite number, that's not 0, right? Then a sub n, the one we don't know, will always do exactly what b sub n does, the one we do know. So this a sub n will be the given part. This b sub n will be the one we come up with. And we're only going to come up with things that we know what happens. We're going to make a ratio, we're going to take a limit, we're going to hope it turns out to be something that's not 0 or infinity. And then if we know what happened to b, we'll know what happened to a. Okay, so that's the best case scenario. Still okay, but not as great. If we take the limit as n goes to infinity of a sub n over b sub n, and it equals 0, and if b sub n converges, right, then a sub n will also converge. So let's talk about that one for a second. So if this limit goes to 0, then we know that b sub n grows bigger faster than a sub n, right? That's how you get this ratio to go to 0. So if b sub n is bigger, and b sub n converges, then a sub n is also going to converge. See the comparison test above. Okay. Here's the other one. If it equals infinity, right, the two things we excluded in our first test version. So if the limit as n goes to infinity is infinity, and b sub n diverges, then a sub n also diverges. Okay, so let's talk about that one. So this time, right, it's diverging, and so what that means is that a sub n is going to be bigger, right? A sub n is bigger than b sub n. And if b sub n diverges, right, then this series that's bigger than that is also going to diverge. Okay? And again, if-then statements only work in one direction. Okay, so let's go ahead and practice that. I took that page out. Determine if it converges or diverges. So let's take a look. What do we think? So what would we compare it to, right? It kind of feels like a 1 over square root of n, right? So we're going to choose b sub n to be 1 over the square root of n. Okay. But I'm not going to do the inequality. Now I'm going to do this with a limit. Okay. So I want to take the limit of the one that I'm given, 1 over square root n plus 1, over 1 over square root n, as n goes to infinity. This b sub n that I've chosen, I know diverges because it's p series. And what's p equal this time? Right, 1/2. So less than 1, so diverges. Come down here and let's do our limit. So as n goes to infinity, a couple of ways you can do that. I think I'm actually just going to simplify that complex fraction. So I'm going to bring that 1 over square root n up and over. So I've got square root n over square root n plus 1. A couple of things. I guess we could divide through by 1 over square root n at this point. You can also just look at leading coefficients. So limit n goes to infinity of 1 over 1 plus 1 over square root n. So that 1 over square root n goes to 0, so my limit equals 1. This is your L value, right? So this, right, we're in the situation where the limit equals a number that it's 1, it's not 0, it's not infinity. So a sub n and b sub n both do the same thing. B sub n diverges, therefore, I left off my 1 to infinity of 1 over square root n plus 1 also diverges. Didn't leave myself enough room to write that out nicely. But I've got all the pieces in there. I know what L is, and I know that B sub n diverges. Okay, let's try one more, last one. So I have the series n 1 to infinity, 2 to the n plus 1 over 3 to the n. Okay, we're using this limit comparison test. So this is my a sub n. I'm going to come up with a b sub n that we know something about. So what does this, right, they should give you kind of a flavor. It's like, gosh, what does this feel like? To me, it kind of feels like a 2/3 to the n, which is a geometric series, right? Common ratio. That r is 2/3, which is less than 1. So we know that my b of n converges. So if the limit of the ratio goes to a number, then we know that a sub n also converges. So now we're going to look at the ratio again. I shouldn't say the fraction. So we're going to take the limit, and I shouldn't say ratio because there's a ratio test we're going to get to. Limit, n goes to infinity. So I'm going to do a sub n over b sub n. I'll go ahead and split that apart. Okay. As n gets big. So go ahead and flip. N goes to infinity. So this, right, this bottom fraction is going to flip and multiply. I'll go ahead and I'll write out the algebra. 2 to the n plus 1 over 3 to the n times 3 to the n over 2 to the n. Okay, so my 3 to the n's can cancel. So now I'm taking the limit as n goes to infinity of 2 to the n plus 1 over 2 to the n. So this is going to be 1 again. Right, so here's your L. Right, 2 to the n plus 1 over 2 to the n. This plus 1 isn't contributing anything at all. So it's really just 2 to the n over 2 to the n, which is 1. So since the limit, right, of a sub n over b sub n equals 1, and b sub n converges because it's a geometric series with r less than 1, then the series we were given, 2 to the n plus 1 over 3 to the n, also converges.